right? We're good? Okay, Iapetus, guys. So when you look at Iapetus, the first thing you might notice is this albedo contrast. You can see it here in the Voyager images, and of course this dark splotch here is actually real. And as we got to see it with Cassini, you can see that there's a lot more detail. Now, I cheated a little bit. I couldn't find exact disk images here, so you'll see that this is mostly dark, right? So it's not totally rotated perfectly, and this is kind of falling off the edge. But you get the point, right? Like, Iapetus has a lot going on. The first thing you'll notice is the albedo contrast, but the other thing that was very surprising coming out of Cassini is it has this equatorial ridge. Can you guys see that? That's on the equator, like not like 20 degrees. It's like on the equator. And this is a perspective image. This is a three-dimensional model that was built from a few different images, stereo images. It's actually quite tall. It goes all the way around. In the bright areas here, you can see it right in here, and it starts to taper off. It's a little bit harder to see in here, and we think that's just because it's been sort of bombarded from impact craters, and it hasn't been preserved as well there. But you can see it here on the dark side also. It's this huge ridge. Iapetus is covered in these huge basins. And to show you two different images, I was trying really hard to put this on one slide so it would look really cool. So this is one image here. And you can see that you've got this dark, turns out it's carbonaceous material. It's got a lot of carbon in it. That's all I know about it. I'm a geologist, not a chemist. But you get a lot of carbon here. It's really, really dark. And then you've got this super bright white snow colored, right? It's as bright as snow material. And so you tend to find the dark stuff in the floors of these craters. There hasn't been a ton of work on this sort of contrast other than they've measured it and they've measured the spectra of the different composition of the dark material. Trying to figure out what's going on. They think maybe it's a lag deposit, so maybe some of the bright material is sublimating away and some of this dark material is being left behind. Of course, you still need a reason for that sublimation to be happening, preferentially on one side versus the other. But this is a really curious observation that they've made about Iapetus. We knew about the bright-dark dichotomy, but we didn't know that it went down to this scale. And so this is something that's really interesting and intriguing, and I think there's still a lot of work to be done, and it's probably going to take another trip, because, of course, Iapetus didn't get an awful lot of flybys. And so there's still a lot more data that needs to get collected here. So I want to move to Titan. I think some of these pictures maybe you saw because we don't have a ton of pictures of Titan from the surface, namely this one. And I couldn't decide between the colorized and the non-colorized, so I gave you guys both. So the colorized is a false color image, but they tweaked it because they wanted it to look like what you would see if you were standing on the surface of Titan. These images are from the Huygens probe. Because Titan has such a thick atmosphere, we can't use the Cassini camera in order to take photographs of the surface, so they use the Cassini radar instrument, and I will show you some Cassini radar pictures. And so that's what made this particular image so special, was because it was taken from a camera, from the probe, on the surface. It took a lot of atmospheric measurements on its way down through the atmosphere, and so it didn't do an awful lot of photographing of the surface. Yes?
That there was audio taken, that it was near some type of creek, but the creek was made of methane, and they actually had the audio of the trickling methane.
A methane creek I would buy. I don't know about the audio. That's the first I've heard of it. I actually looked for the equivalent of, has anybody seen the YouTube video 7 Minutes of Terror? And it's the photographs that the Curiosity rover were taking as the sky crane was lowering it down under the surface. So I found that video, and I swore that there was a similar video for Titan, and we couldn't find it. And so that's what I would have, I didn't see that, but I should look into that because I haven't heard that. But creeks of methane, totally possible on Titan, and I'll show you some pictures about why we think that's possible. And then this is just a really great picture that Cassini took with the camera, and you can just see it's really dense atmosphere, which produces really cool. This is a storm, yes. Okay, so these are radar images, so they're not exactly the same as a photograph. But why we think methane creeks might be a totally legitimate possibility is because when you look at something like this looks an awful lot like Earth, right? I mean, you sort of have these dendritic valley networks down through here. Because this is radar, dark things are going to be really smooth, bright things are going to be really rough. That's what radar tells you. And so when you look up here, you actually see these really long longitudinal dunes. And these you find all over the equatorial regions on Titan. And so the fact that Titan has dunes, which means it's got some kind of granular material on the surface, you need wind to make dunes. So it's got a really active, dynamic environment and atmosphere that's going to help produce these dunes. Of course, people have used these dunes to try and reconstruct what they think the wind patterns of the atmosphere is doing at the time these dunes were forming. But then, of course, you have these lakes. And the lakes have been a really cool area that's of interest, in part because there's been so many Titan flybys by Cassini. Of course, when we looked at that chart with all the different orbits for each year, Titan almost dominated every other satellite in the system. Of course, Titan was a big target for the Cassini mission, and that's one reason they have so many Titan flybys sort of scheduled in. But it also gives them the opportunity to do time-lapse. And what's been really cool about the time-lapse is when you look at the time-lapse around these lakes, you actually see changes. And so you can see this oval sort of identifies that there's nothing here, and then there's something here, and then there's more of that something over here. They think this may have to do with seasonal changes, where some of that material is going up into the North Polar caps in the wintertime and then coming back down in the summertime and filling those lakes. And every time I see different montages of Titan's lakes and changes over time, it's always fascinating because it means that Titan is active. I mean, it's geologically, not hydrologically, but hydrologically active. There's a fluid system, likely methane, ethane liquids on the surface that are moving and flowing and eroding the surfaces in much the same way you see here on Earth. I have a couple more pictures of Titan later, I promise. But I want to move a little bit further into the Saturnian system so I don't totally run out of time here, because I can't pick my favorite satellites, so I'm trying to show you all of them. And that's really hard to do in the time frame that we have here. So Dione is actually a moon that I've started working on recently when I started working at the Smithsonian. And one of the things I thought was super interesting about Dione are what are called these wispy terrains. And you can see here in these really smoothed photomosaics from Voyager that you see all these kind of tendrils in here, and they were just these bright linear things that some people sort of thought, well, maybe they have to do with volcanism. Maybe there's this material that's being kind of draped on the surface. They weren't really sure, and when Cassini flew by, you actually got to see that there are these huge tectonic features, which for me was kind of a big deal because I really like cracks. And so, you know, you see that Dione's surface is on one side in particular is just covered in these fault scarps. And the face of these fault scarps are bright white. So that's actually what was giving them this sort of wispy, bright appearance in the Voyager data. And it's the Cassini data that actually showed us that it's this huge tectonized region, which means something happened on Dione on just one side, but not the other. And I'm still trying to figure out what that meant or how that happened. So stay tuned, hopefully. So Dione's been a really interesting one in particular because it has all this tectonic activity on it, which in my opinion is kind of only matched by Enceladus. And I'll show you some more pictures of Enceladus and how heavily tectonized it is in some regions. But here's a close-up, zoomed in a little bit, and you can start to see some of these linear features. And here are very discrete rather than being diffuse. And if they were kind of more diffuse, you would think, okay, maybe it's some kind of particulate material that's being draped on the surface through volcanism or something. But when you zoom in even more, you can actually start to see that these things are actually scarps. They're these offsets. So I want to get into Tethys, which I feel like some of the Saturnian moons, because they're so heavily cratered, aren't always considered particularly interesting, but they all have their own unique special quality. And Tethys is one of them because it also kind of has this wispy terrain depending on the lighting conditions. And so you can see the Voyager images and how dramatic these sort of like smoothed, enhanced photomosaics are. And you can see there's this large crater here on the surface of Titan, and then I believe this is called Ithaca Chasm, right down in here. And you can actually see it here in some of the Voyager data, but we're now starting to see this in way better detail. And you're actually able to, well, there was no targeted stereo on Tethys, which means taking image pairs specifically for the purpose of building a digital elevation model. There's actually just enough coverage in certain parts of Tethys right along Ithaca Chasm where you're actually able to build a digital elevation model and actually look at its elevation. But it's another really cool tectonic structure on Tethys that, because everybody's been so romanced by Enceladus and Titan, not as many people have been working on Tethys. And so this is an ongoing area of study for a lot of people who are still digging their way through all the Cassini data that's come down. Another really interesting thing about Tethys are what some people have shown to be these red streaks. Now, these are color images of the surface of Tethys. Of course, they're false color. But they actually find these very discrete red streaks across the surface. And when you compare them to the surface geology, they have no geological expression. There's no different colors there. There's no tectonic structures. There's no impact ejecta. There's nothing to indicate what the origin of these features are. So this is another ongoing mystery with Tethys. So even though a lot of people are like, nah, it's just full of craters, it's actually got a lot of its own stuff going on that we still don't have an answer to. Okay, Enceladus. I'm a little biased. I've spent a lot of time studying Enceladus. I still study Enceladus. But as you can see from the Voyager data, we didn't get an awful lot. And so to try and get your eye in, there's sort of this bump here of a belt of fractures, which is this one right here. And then this sort of polygonal set of structures here are right in here. I don't know if the contrast is good enough. And these are actually ridges. Now, in icy satellites, ridges are not a super common tectonic structure. So when you put a bottle of water in your freezer and you fill it too full, what happens? The lid gets popped off. So when water goes from a liquid to a solid, it expands. When rock goes from a liquid, lava, to a solid, it contracts. So places like the moon and Mercury, you see thrust faults everywhere. Icy satellites, you don't see a lot of thrust faulting. You see a lot of tension cracking and normal faulting, all things that happen in tension when things are being pulled apart. Because at one point, these balls of ice used to be liquid, right? And as that liquid has frozen over time, it cracks because it's expanding. So you actually see predominantly tension fractures, cracks all over the surface of these bodies. And so when Enceladus showed up with these huge ridges, we were so surprised, and we still have no idea why they're there. And so Cassini brought back these really amazing images where from, these images, you're like, okay, Enceladus has some cool stuff going on, but we're missing most of the data. And of course, Enceladus has become one of the biggest targets for Cassini, and of course, now we have amazing data all over the place. Some of the other interesting things about Enceladus, of course, is its south pole, right? Everyone wants to talk about Enceladus' south pole because it's this tiny moon that's geologically active. You have a question, young man. Why are the planets round? That's an excellent question. So the planets are round because they have enough mass to have enough gravity to start spinning, and that pulls them all into a tight sphere. That's the best way I know how to explain it. And so some bodies, like the asteroids, they're not big enough to have enough gravity to pull themselves into round shapes. And that's why a lot of the asteroids look kind of like baked potatoes or kind of like weird shapes of dirt balls. So Enceladus is still big enough to be round. It's got this south pole. These are what are called the tiger stripes for many obvious reasons. They sort of look like stripes on a tiger. And this is where all the material is being shot out in space, creating the E-ring. What's really fascinating about Enceladus, though, is this is the North Pole. There's no tiger stripes there. There's no plume there. But to make something hot on one side and not hot on the other side is actually really, really hard to do. And so people have been modeling like crazy, trying to figure out why Enceladus is hot on one side and not on the other. Now, in my opinion, there's something interesting going on in the North Pole because all of these small cracks that you see here are really quite young. So if, in fact, the North Pole is as cold and dead as everybody thinks it is, we shouldn't have these really young, small fractures occurring in the North Pole. Yes, sir? So we're not. So the tiger stripes are, in fact, a region of brittle failure in the ice shell. It's that underneath those tiger stripes, we have a reservoir of water. Well, but there's no liquid on the surface. The liquid is in the subsurface. So at some point, by the time that liquid is actually exiting those tiger stripes, you're actually looking at solids. It's like snow. The reason these are showing up blue here in the false color image is because of a grain size difference. Yes. Okay, so as I've been saying, Enceladus has this warm south pole, and so before Cassini reached Saturn, they were trying to figure out how they would see the thermal structure of Enceladus, what they would predict to see. And so this is, of course, what you would predict to see. It would be warmer in the center areas and colder on the poles. And, of course, they got the exact opposite, which was a huge surprise. And as they approached closer and they saw the tiger stripes and they saw the plume, of course, this all started to make a little bit more sense. But still the underlying why is it all happening and why is it all happening in the South Pole still hasn't been fully answered. And so just to kind of bring home exactly where the heat is coming from, we've actually done observations such that you can actually see that the heat is very directly related to these individual structures. Just in case you didn't believe me that the hot stuff was coming out of the tiger stripes, it is. The other thing that's really interesting that's come out, this is a schematic of what we might think the interior of Enceladus looks like. We think that perhaps the ocean is a little bit thicker on the South Pole, and that, of course, that it goes all the way around. And what's really cool is, this might be a little bit subtle, this blocky pixelated image, this is Enceladus here, and then these brighter pixels down in here are the plume. And you can see that they're brighter here and less bright here. And so what's actually showing you is that because Enceladus is in an elliptical orbit, those tiger stripes we think are flexing, open and close, open and close, open and close, and that's actually controlling the amount of material that's being released. And you can actually measure that in brightness. So this was a particularly cool result, and I remember seeing this image being like, nah, that can't be real. But it is, and that's pretty interesting, the fact that we've been able to tie at least tidal flexing, the force of Saturn pulling on Enceladus is changing because, of course, Enceladus' distance around Saturn is changing. And so that amount of pull is changing through its orbit. And you can actually see it happen and see it affect the plume. And I think that's been a pretty exciting result from the Cassini data. Yes?
Is the plume getting lost in the space, or is it going back to it?
So a lot of the material, the larger particles, fall back onto the surface. About 10% of the material coming out of the plume gets lost into the E-ring. Much of the E-ring material does eventually find its way back onto Enceladus. So I don't have an awful lot to say about Mimas, other than it is in fact a moon, and that this crater is named Herschel. And craters on icy satellites tend to be a little bit strange. They tend to be flatter than we would expect them to be, in part because of how craters form in ice. And the fun factoid I love about Mimas is that if the impact event that created Herschel had been just a little bit bigger, we wouldn't have a Mimas. And so I always think that it's sort of the little moon that could. It managed to stick together through the large impact event. Plus, everybody loves this. Okay, so we've been moving our way in closer and closer towards Saturn. Hyperion is actually out past Iapetus. But I'm starting with Hyperion here because I'm starting to move into all the really tiny moons that Saturn has that I'm not sure everybody's really thought an awful lot about, in part because we haven't seen them yet until this plan for Cassini's finale has started. And so Hyperion's really weird. Its density is about 0.6. Density of water is 1 for reference, which means if you were to put Hyperion in a bathtub, it would float. We think it's because it's as porous as it looks. So it looks like a giant sponge. We think it probably is. Why? We don't know yet. But it's pretty spectacular, right? It's super weird. And this looks like, this is a giant impact crater here, and then you can see all these little impact craters inside of it. So I put it up for a little bit of an awe factor because it's pretty excellent. But this is another montage from the Planetary Society. I don't know if anybody follows Emily Lakdawala on Twitter, but she makes the best images for the Planetary Society, including these posters. So this is a scale image of Hyperion to all these other really, really tiny moons. And I'm going to show some of them to you up close, including Pan, Prometheus, and Pandora. And I want to start with Pandora and Prometheus because they are what are called the shepherd moons. So this is Pandora here, and this is Prometheus here. And what they're doing is they're sort of shepherding or protecting this ring, which is called the F ring. I hunted and hunted and hunted, and guys, I gotta tell you, nobody would ever tell me what moon this was. I'm pretty sure it's Epimetheus, but I'm not 100% on that one because everybody would only talk about Pandora and Prometheus here. But so this is the F ring, and they're trying to figure out how these moons are actually keeping that ring in place without kind of getting absorbed and sort of ripped apart by Saturn. And there was a paper that came out in Nature like a couple weeks ago, and I didn't have time to read it. But I thought that not only was this a spectacular image, it's pretty cool to think that these two little tiny moons are actually affecting the structure of Saturn's rings.
Now, the inner one, of course, should be orbiting faster than the outer one, but are they actually locked in sync for some reason?
I don't know the answer to that.
Okay.
So many of Saturn's moons have resonances with one another, but I actually didn't get that information yet. It's very possible because many of them have relationships with one another, but I'm not 100% sure on this one. So as I was digging through trying to figure out more about Pandora and Prometheus, I found these sort of closer up images of them that I thought would be really interesting to show you. And I think Pandora sort of looks maybe the way you would expect a tiny moon to look. It's kind of lumpy and potato shaped. But I thought Prometheus was really cool because it's got this sort of thing sticking out of the side of it and sort of this, I don't know, it kind of looks like a meringue. But they're weird and they get weirder, right? Because you've got Hyperion in sort of different places around Saturn, and then you've got these strange little moons, but they get weirder. So I mentioned over here that, there it is. That's Hyperion, that's Prometheus and Pandora, but I want to show you guys Pan because when I saw the picture of Pan come out in the news, I don't know if anybody saw it, blew my mind. Okay, so we're going to talk about Pan because, of course, Pan was in that other image, but now it's one of the big moons in this montage, also by the Planetary Society, where you get down to these teeny tiny little moons that until Cassini, we knew, I think, most of them existed, but of course we didn't have a clue because they're pretty hard to see because they're pretty tiny. Okay, so Pan was lovingly called the space ravioli, the space empanada. I saw the space pierogi, and my favorite was the cosmic dumpling. So it's such a strange little moon because it's sort of this moon with this debris ring around it, sort of like Iapetus, but the proportions are all weird, right? And to get something that tall on a body this small is actually really hard. And then, of course, me wanting to look at the faults and fractures, I'm really intrigued by these. So they're all parallel with one another, which means they probably all formed at about the same time due to the same mechanism. If anybody has any ideas, I'm waiting. Right? I know. So I'm still not sure what's going on here, but what they think is actually happening is really well described in this picture of Daphnis, is they actually think that as Pan is moving around Saturn, it's actually collecting material onto its edges, coming off of the rings. And I think this Daphnis actually is very similarly shaped to Pan. It's sort of this saucer-shaped thing with this big ring of debris around the sides of it. It's really steep-sided too, which makes it hard to imagine how it collected material and actually sort of stayed there, because the angle of repose would be really steep. So you've got Daphnis making waves, and this is one of the images that they captured. I want to say this is from April. So they're already in the process of sort of the Cassini finale. And you've got Daphnis actually affecting and changing the shape of these waves. And I thought this was not only a pretty spectacular picture, but I thought it did a really good job of illustrating maybe why Pan is shaped the way it is, because there's more of Saturn's tiny moons that have that interesting structure. So why would we end such an awesome mission, right? There's so much interesting stuff that's coming down from Cassini. So what gives? Why would you just end something that's happening? And we can't blame it on funding in this particular case. And we have to blame Enceladus and Titan. So this is another cool picture of Titan. This has been smoothed. They call it despeckled, is sort of the new tool that they've been using to interpret Titan data. And I think more than any of the other Titan images that I've shown you, this looks really Earth-like, right? I mean, you've got these really detailed fracturing valley networks that look an awful lot like the kind of thing you would see here on Earth. And then, of course, this lake here. And then I've always loved this image of Enceladus because even though it's kind of low res, you can actually see the texture of Enceladus' surface. You can see that there's almost no craters there, which means it's highly fractured, it's very young, and then it's really hazy, which isn't bad processing. It's actually the plume material that you're looking through. So you have these two moons that are drastically different. Titan is one of the largest moons in the solar system, next to, say, Ganymede, one of Jupiter's moons. And Enceladus is perhaps not one of the tiniest, but it's really small to be this geologically active. So you have two incredibly active places. So what am I getting at, right? I'm getting at astrobiology. Enceladus is warm, it's got clearly some liquid somewhere inside of it, and you've got Titan that has liquid on the surface. It's one of the only other, no, it is the only other body in the solar system with flowing liquid, moving active liquid on the surface. These are two hot astrobiological targets for future missions. So as the Cassini mission is starting to lose fuel, it's actually starting to lose its ability to maneuver itself around the system. And the last thing they want to happen is for Cassini to accidentally fail and crash into one of these two moons. So you can blame these two. But they're trying to make lemonade, right? Because they're going to get to do some really cool and in many cases risky science. Because who would dare take a couple $2 billion spacecraft and dive it between Saturn and the inner ring, its innermost ring? That's really risky. There's a lot of debris there, but we can do some really exciting science because if we're this close into Saturn, worst case scenario, if we don't get to finish Cassini's finale, it's going to crash into Saturn anyways. So we've brought Cassini into this point where it's actually in kind of this safe zone. And so you can actually do some really interesting science here that maybe you wouldn't have done otherwise because you're pretty risk averse when you've got a few $1 billion floating around in space. So it's going to be able to look at Saturn's gravity, its magnetic fields, the internal structure of Saturn. I didn't mention Saturn's also has a density of less than 1, so if you had a bathtub big enough, Saturn would also float. It's going to try and pin down its rotation rate a little bit better also. It also wants to try and do a better job of understanding how much more material is in the ring and a little bit more about ring formation that they can do from this really unique perspective. And they also want to sample these ring particles that are sort of falling into Saturn's atmosphere. They're getting kind of pulled into Saturn through the magnetic field. And so I really like this infographic here where it shows you where Earth is looking, where Titan's orbit is, and where all these finale orbits are going to be. And so what it's going to do is it's going to complete all these orbits diving deep into between the rings and Saturn here, and actually measure what's called the D ring, which is the innermost ring. Saturn's rings are labeled in alphabetical order in order of discovery. So of course the E ring was the eth number to be discovered. It's not because it's named after Enceladus. The D ring is the innermost ring, which isn't logical, right? You would want them to be the innermost would be A, but that's not how it works. And so they've actually varied these orbits, and so you can actually see that they're going to be sampling different parts of the D ring in these 22 orbits. So they get to do some really exciting, really interesting science, and more importantly, they get to take awesome pictures so that we get to enjoy them. I don't study rings, but when I think about the fact that people who do study rings are having this really cool moment, there's not going to be another mission to Saturn for a long time, and most likely, unless we get really lucky. And so, you know, when you talk about rings, of course, Jupiter has rings and Uranus and Neptune have rings, but they're nothing like what you see at Saturn. And so you get really cool pictures like this, and I think that's going to be pretty exciting as we lead up to the next few months and the finale on September 15th. So I have 3 more slides. This is another awesome picture that you might expect. This is the last time Cassini will photograph the Earth and the Moon. And this is through the rings, of course. So this is a pretty spectacular image that I was going to leave as my last slide, but I'm so excited about the outer solar system. I wanted to give you guys all something to look forward to. So not only do you have September 15th of this year to look forward to as the last day of Cassini as it heroically plunges through the atmosphere of Saturn to collect even more data for us. There's more on the horizon. New Horizons, sorry, didn't mean to do it. So New Horizons, as many of you probably know, was a flyby mission in 2014. Flyby past Pluto. 2015, July 14th of 2015. I get it sometimes a little mixed up. So you've got the New Horizons spacecraft. What I think a lot of people don't know about New Horizons is that it wasn't designed specifically as a Pluto mission. It was designed as a Kuiper Belt object mission. So while Pluto was the first Kuiper Belt object that New Horizons was to encounter, it was always designed to go past Pluto and study other Kuiper Belt objects. And so January 1st of 2019, New Horizons is flying by another Kuiper Belt object and will send that data back. And it will be as spectacular as what you saw at Pluto. So this is something in the very near future that I think is worth keeping your eye out for. We also have the Europa Clipper mission. We think that Europa Clipper will probably launch sometime in the early to mid 2020s. It's all going to depend on how its development happens, what rocket they can get to launch it. There's a lot of talk about what rockets they can use, what they'll have available to them. But the Europa Clipper mission will go back to Europa, one of Jupiter's moons. And we think Europa is a phenomenal analog for Enceladus and ocean worlds in the outer solar system in particular. And because we've really digested a lot of the data that came back from the Galileo mission, it's really the right time to be going back to Europa. And if you want to look further into the future and be extra optimistic, which I definitely am, NASA just completed a very large mission study to go to the ice giants Uranus and Neptune. Of course, for me, both of them have really beautiful and interesting suites of icy satellites. Of course, Neptune has Triton, which we also think is a Kuiper Belt object, or originated in the Kuiper Belt. And then, of course, Uranus has a wide collection of moons like Miranda, which have these really crazy tectonic chasma that are just very weird and strange, and I highly recommend that you Google them. That'll be the teaser because I didn't put a picture in here for you. So my last hope is going to be these ice giant missions, and some of them are getting ready for maybe launch in the late 2020s. Or the early 2030s. And so that's actually, when you talk about outer solar system science, and you talk about, Cassini was being thought of in the early 80s, and it launched in the late 90s. I mean, they're expensive. They take a long time to develop because they have to be in space for a really long time. I mean, New Horizons was cruising for over 9 years just to get a flyby of Pluto. So they're big, they're expensive, they're really hard to do. They take an awful lot of time in planning. But when they're really successful, they're really pretty spectacular, as you can see by Cassini, or, if you want to talk about Voyager, they're still going. And they're still pinging little tiny bits of data back to us. And they were hoping that Voyager would be that successful. I mean, that was something that they talked about in the planning stages. And I think that is a testament to the engineers and the scientists who put these missions together. The outer solar system is a hard place to get to, but I think it's really worthwhile. And so I hope that you guys enjoyed this talk, and I'd be really excited about taking any other questions that you guys have about all of this. Yes? Out there. So it depends on what rocket it's on. But both the Uranus and the Neptune orbiters were spec'd out to be on the SLS, which is the Space Launch System, which is the new heavy lift rocket that's in development for the next generation of human spaceflight. So it's being developed for human spaceflight, NASA's next human spaceflight program. But as outer solar system scientists, it's a really attractive rocket because not only can it lift heavy loads, it would allow us to bypass gravity assists. And so, for example, if Europa Clipper launches on an SLS, we'll get there in about 3 years. If we launch on the Delta something, Delta 4, then perhaps it would get there in 5 or more years. So when we're talking about these, we're talking about launching in the 2020s or the 2030s, and you're talking a cruise of about 5 to 6 years if you're on the SLS. So for somebody who knows, these kinds of missions to take 20 years, 25 years to actually get off the ground, these timelines are incredibly optimistic. Now, maybe they're incredibly optimistic, but I like to be a little bit more optimistic than pessimistic. I think for a little while we were concerned that we were going to be radio silent in the outer solar system for a long time.
So there's 2 separate missions?
So they spec'd out both missions. just to decide which one would have the biggest science return, what kind of costs you might anticipate, what kinds of science questions you might ask. So these aren't specific missions for a specific spacecraft. It's what are your target science goals, what are your minimum science goals, how much do you expect that might cost, what kind of timelines are you looking at, what kind of instrumentation packages would you want. But typically these missions get competed, or at least the instruments get competed. So this is more of a guideline of how you might actually make something like this happen. I saw another hand. Yes, sir.
You mentioned, I guess, ridges, and I think Enceladus, and you said they were probably caused by thrust faulting due to expansion of, I guess, liquid water turning into, as it turns into ice, and you have a space problem on the surface. Is that?
No, so actually the expansion would cause more like normal faulting, and that's what makes the ridges on Enceladus really unique, because typically ridges would often form under compressive environments like thrust faulting, and so you wouldn't expect to see things like ridges on these icy satellites. So they're more of an anomaly.
Okay, so they're unexplained.
They're unexplained.
On most of these icy planets, it's easy to find rim zones, but unless the planets are, or the moons are expanding, you've got kind of a conservation of mass problem.
Well, so as long as your volume changes, you can conserve your mass. So if the diameters of these things change a little bit, then you've conserved your volume and you're not gaining any more or less mass. And because this is all happening on the surface, you're probably okay. Now, to throw a wrench in the idea, there was a recent paper in the last couple of years about the idea that there may be zones of subduction on Europa. Now, if you've got zones of subduction, you don't even have to change your surface area, right? Because as you make some material, you can subduct it. Now, I'm not saying plate tectonics, although some people like to use that word. But zones of subduction would solve a surface area problem. You'd be able to maintain your surface area. We haven't found evidence of that on Enceladus, but generally, you know, it's okay for your surface area to change a little bit in these instances because it's happening on the surface.
So they do acknowledge that they are maybe expanding.
A little bit, yeah.
Are the carbon compounds, is it called tholins?
There are, yeah. So there are a lot of tholins that have been observed on the outer solar system satellites in particular. So a lot of the dark areas that you're seeing are likely to be tholins.
So what is that material in the E-ring that's being ejected? What is that?
Mostly water. There's other kinds of yummy little organic things which make, you know, Enceladus a really exciting place to go back to for astrobiological studies, trying to understand whether or not it's really habitable because of these additional organics in there. When I say organic, I don't mean biological. I just mean that they're organic compounds. Like tholins are often organic compounds, but they're not biological in nature. We think Enceladus's ocean is a little bit salty, and it's got these other compounds in it, so they think Enceladus's ocean might actually be a region that is potentially habitable, not habited, habitable. And so it's mostly water ice that you're seeing in the E-ring. I don't know the answer to that question. Yes, sir.
Is there an estimate of the total mass that came from Enceladus to form
The E-ring.
And would that have been significant for the evolutionary history?
Yeah. So this is a really interesting, multifaceted question. The first answer is I don't remember the mass flux that's coming out of the South Pole and the mass that they've estimated for the E-ring, but those estimates do exist. For a little while, you know, you started looking at the numbers and you're like, shoot, Enceladus shouldn't be there anymore because it's actually ejecting a lot of material. A lot of those ice grains are falling back onto the surface and actually blanketing a huge fraction of Enceladus's surface in essentially snow. So we think there's a very thick eye in particular. You can look up my paper. I wrote a paper about this. I actually think the surface is covered in a very thick layer of snow. Much of that is fallback from the plume material that's not traveling fast enough to escape Enceladus's gravity. It's really the small, fine-grained particles that are actually escaping into the E-ring. But even some of the E-ring material is coming back onto the surface. So the second half of your question is sort of what's the fate of Enceladus? And there's a lot of debate about how long the plume has been going. Is it ongoing? Are we really special? We're seeing Enceladus at a really special time in its history. Or has it been ongoing its entire history, and there's some other processes that are going on in order to make this sustainable? We don't know the answer to that yet. I think most people like to think we're being really special, but when it comes to space, I mean, you guys know, stuff's far away, it's really old. You know, to think that we're seeing Enceladus at this special sort of snapshot in its history is hard to wrap your brain around when you consider how short of a period that probably is. So it's complicated, and everybody's thinking about it really hard.
2 questions.
Sure.
First one is probably pretty simple. What happened to the Huygens?
Still there.
Still there?
Yep.
Still doing things?
It did stuff for, I want to say, it's either 20 minutes or 2 hours, and I just remember the 2. I don't remember how long it was. It was not long.
Okay.
But it's still there, but it didn't do much after. Once it landed, it did its basic experiments, and it hit its primary science goals, and I think that's the most important part. So, of course, most spacecraft missions, well, any robotic mission has its primary science goals, and then it's got its secondary science goals. If you can meet your primary science goals, it's a big win. So it met its primary and probably some of its secondary science goals. What was the second?
So the second question is the Pan, I think, the one that's accumulating weird material on the outside.
Sure.
Is there some thought that there's maybe a sort of cyclical process of this where these bodies will accumulate material from the rings and then get ripped apart and then accumulate material from the rings? And so maybe we're just seeing like, you know, a weird accumulation that's going to get separated again at some point?
I haven't heard that idea specifically in the context of Pan, but there was this interesting idea about the shepherd moons, where they think there's some kind of cyclic process that's going on that allows them to be stable. And they did that specifically for the shepherd moons, Pandora and Prometheus. But I would not be surprised if it fits for things like Pan and Daphnis. I think I suspect those papers are actually probably very close to coming out because that data came down, in the last 6 months, but I haven't seen it yet. But I wouldn't be surprised because when you look at those angles of repose, if that's really material collecting off the ring, that is loose, unconsolidated material. And for it to be stable there feels really unlikely, right? And so the idea that maybe it sloughs off and then accumulates some of it and then sloughs it off again actually seems a lot more likely that it's not a stable process.
Thanks.
Yes?
You mentioned some ideas about subduction somewhere.
Europa.
Subduction going on. What would be the mechanism? What I know on Earth, I think I know, is the heavier thing dives and then the lighter.
Yeah, so mechanically it's really hard because what happens when you put ice in your glass of water? Floats. Yeah, so to subduct ice, solid ice into what I always envision as a Slurpee underneath, sort of a not solid, not liquid. They call them slushy brine. Everybody likes to come up with their own inventive way of describing what the mantle might look like, right? But essentially it's a Slurpee. To get solid ice into that is really hard. You have a big density problem. So to get this material to subduct is a problem that they're working on. I've seen some of the evidence for it, and I have a colleague he's got like this group of like 15 interns working on this project. It's really convincing that there is chunks of the surface missing. And if you're not subducting it, I don't know how you it's like scissors, right? It's like they cut it out. There's these really discrete boundaries and there's something missing there. But there's a problem of how do you get it to subduct? Everybody's thinking that it happens the way you're thinking. You've got the slab and it's getting pulled down. I don't know how you get it there. We think we know how the crust is forming because we've got these large things called bands, which are these really smooth, flat, sort of symmetrical areas that just look like they're doing this. So we have regions on Europa where we actually think new crust might be forming, but again, you have this problem of how do you make sure your surface area isn't just like expanding and creating weird things that aren't possible in the subsurface. So it's a really good question, but this idea of subduction on Europa is really new. People are excited about it, but they have a healthy skepticism for it, and so I think this is a problem that people are working on. Other questions? Yeah. Duke it out.
No, that's fine.
So you mentioned it, I'm sorry.
That's okay.
Shrinking
Yes, red streaks on Tethys.
So, Cassini's got an imaging spectrometer. What does the compositional data show? I mean, what does it show as far as the spectral analysis, as far as composition?
As far as I know, at that location on Tethys, we don't have any spectral data. You're right, it does have a spectrometer on it. So I didn't have time to mention this because you can't mention all the things about Cassini. One of the things they did to cut costs on Cassini was they eliminated its scanning platform. So essentially what that allows you to do is it allows you to run a variety of instruments at the exact same time. So you could take a photograph, you could collect some color data, and you could take some spectra of it. Cassini's notoriously really hard to drive. I mean, you're not driving it, but you know what I mean. It's really hard to maneuver this spacecraft because it doesn't have this scanning platform, which they ended up cutting because of cost and weight restrictions and power and all the things that you have to consider. So I suspect that's one reason we don't have the spectral data.
So you have to talk to both of our reps and use anything?
Yeah, it's great. Zach?
That's the ice question.
Sure.
So you keep saying just water ice.
Yes.
Is it possible that some of this water ice are some of the more exotic forms of ice that we can do here under different circumstances than what we normally do in the season?
Yeah, so at the surface, we're talking ices that are hard to replicate here on Earth, but under the pressures and temperatures that you're getting in space, you're talking about ice that behaves an awful lot like, say, basalt here on Earth. It's that brittle. So when we talk about doing analog experiments on Earth, it's actually really challenging because people are like, oh, you could just go to Antarctica and study the faults there. Well, that ice is surprisingly too warm. And I know it's weird to think about, but the ice in Antarctica is too warm. It's too soft as a result, and it doesn't behave in the same way. So we actually use basalt as a far better analog for the ices. Now, some of the modeling that they've done for Titan suggests that Titan's, below Titan's sort of petroleum-based surface, right, is mostly water ice. And they do think that in the subsurface, much deeper down, you do get some of the more exotic phases of ice. But most of the other planets, most of the other moons, excuse me, I call them planets. I think they're all just as important. Most of them do have, are too small to actually reach those sort of pressure temperature conditions to kind of create some of those really exotic ices.
The follow-up is going to be, would that explain the subduction? Maybe can explain otherwise?
Yeah, I think some very smart people are going to have to put on their thinking caps because I think it's, you know, when the paper first came out, I had healthy skepticism. I still have healthy skepticism, but now that I've seen the observational data, it's really hard to explain it without subduction.
Brief,
Yes.
brief break. Chris reported that there's a report of a severe storm coming about the next half hour. If anybody needs to secure their camping equipment, you should probably do that now. Otherwise, this is not a bad place to be, so you don't have to stop. But you have to maintain.
But don't be surprised half hour, it's gonna rain.
I know, right?
What makes Neptune blue? It's Neptune that's blue, right?
Well, they're both blue. No, it's bluer.
Yeah, it's just, I mean, it always is really blue.
I don't know the answer, in part because